Alright, so welcome to the next video on limits. Its title is Grunt Work, and the premise is that you don't always have a graph to figure out the limit from. And so you need a better method for calculating a limit. And so this is one of two ways to calculate. As you can see here, what we're saying is that more often than not, you don't actually have a graph when I ask you to compute a limit. Mostly, I'm just going to write, compute this limit, and then there will be a limit there in front of you. So you can see here are sort of 9 quintessential examples of limits that you're going to have to compute by the time we're done with the semester. And so the real question becomes, how on earth could you compute these without the graph? And so if we take away graphing, then there's basically two things left that we can do. One of the two things is the method called plug and chug, where you just plug in values of x into your function that are near the value you're trying to evaluate the limit at. And the other is playing by the rules, which is using different rules to compute the limits. Now, the next video is going to be about the rules, but this video is about plugging in values. And since this video is about calculating, and calculating is about finding patterns, what we're going to do is we're going to look at a bunch of patterns and try to figure out together where they're going to. So go ahead and pause your video and look at these patterns and try to figure out for each of the different colors where the pattern might be going. If you're done pausing, let's talk about where these patterns are going. So let's look at the brown pattern. The numbers are increasing, but the amount they're increasing by is slowing down as we're getting closer and closer to the number 2. So these are going to 2. And you can tell that they're going to 2, or at least that they should be going to 2, because we have 1.9, 1.98, 1.997. Each of these are closer to 2 than the previous one, but are not trying to get past 2. Now, decimals are friendly, fractions are friendly. I know that a lot of people are scared of them, but if we look at the next set, 0, 4, 6, 7, 7.5, 7 3/4, 7 7/8, we can tell that these are getting closer and closer to something as well. And what they're getting closer and closer to is 8. Now the next set, the red set, 1/8, 1/2, 2, 8, 32, 128, these are getting bigger and bigger. In fact, each one is 4 times bigger than the previous one. And since they're getting bigger and bigger without bound, we can't write that they are going to something specific, but what we can write is that what they're doing is heading towards positive infinity. Now the next ones have both positives and negatives. But if you look at the positive ones, 8, 2, 1/2, 1/8, and so on, those are going to go towards 0 because each one's getting smaller and smaller. And if you look at the negative ones, -4, -1, -1/4, these are also all going to 0, but from below. And since both of these are going to 0, we think that these are all going to 0. Lastly, 1, -1, 1, -1, 1, -1. We have alternating numbers. When you have alternating numbers like this, the limit winds up not existing. We say that the limit does not exist. And part of that is that if you just take all of the 1s, there's an infinite number of them, and so that would be limiting to 1. And if you take all the negative ones, there's also an infinite number of them, and we would say that those are limiting to -1. And if you can find two subsequences, which are both infinite, which are going to different numbers, then the limit can't possibly exist. And so here are a bunch of different patterns that we can look at and say, okay, well, now that we have these patterns, how do we do some limits? So let's look at a following limit. The limit as x goes to 2 from the right of 3 over x plus 1. Remember, 2 plus means that the values of x are going to be bigger than 2, but not by much. And so let's make a table of numbers bigger than 2, but let's make the table so that the numbers are getting closer and closer to 2 as we go down it. So you can see on the left-hand side I put 3, 2.5, 2 1/4, 2.1, 2.01, and so on. And if we plug those values of x into 3 over x plus 1, the y values that we would get, right, for the function y equals 3 over x plus 1 are 0.75, 0.857, 0.923, 0.968, and 0.997. And just like before, we can ask ourselves, is there a good pattern for this? And there is. These numbers are getting closer and closer to 1. And so what we write is that the limit as x approaches 2 on the right of 3 over x plus 1 is 1. How about another one? We write the limit as x goes to 1 from the left of 2 over 1 minus x. And remember that 1 minus means near 1, but on the left side of it. Right? So we want numbers less than 1. So we make another table. And here's a bunch of numbers less than 1 under x. 0, 0.5, 0.75, 0.9, 0.99, 0.999, right? These are all numbers that are less than 1, but that are getting closer and closer to 1. And if you look at the y values, you can see that the y values keep getting bigger and bigger. In fact, they keep getting bigger and bigger without any bound. The closer we get to 1, the bigger a y value we can make. And the way we write the ability to write something as big as we want is we write that the limit as x goes to 1 from the left of 2 over 1 minus x is positive infinity. So one more. Let's try the limit as x goes to infinity. And this is different. We're not going to a number this time. Instead, we're going out to infinity. And we're looking at the limit as x goes to infinity of 2x plus 1 over x. And remember that when x goes to infinity, right, that means that x can be as big as you want forever. And so we're going to make a table of bigger and bigger values of x. So I did just powers of 10, 1, 10, 100, 1,000, 10,000, so on. And I'm going to plug them into 2x plus 1 over x. Now, to keep things simple, I represented them as decimals rather than fractions, and what I get is 3, 2.1, 2.01, and so on. And you notice that as x gets bigger and bigger, 2x plus 1 over x is getting closer and closer to 2. And so the way we write that is the limit as x goes to infinity of 2x plus 1 over x is 2. And so let's make a couple of notes here. When we're calculating limits, basically you're going to be plugging things in, but you're going to be looking for the same patterns that you looked for when you were graphing. Limits only exist when a consistent pattern can be found. Just like the graph of sine of x, if you're wiggling around too much, you may not wind up ever going to a specific number as we take the limit. The limit as x approaches a of f of x requires you to compute two limits, the limit on the left and the limit on the right. Remember, there's 4 total symbols, the left, the right, infinity, and the one that combines left and right into the same one. The limit as x approaches a without a plus or a minus. Also, the limit as x approaches a of f of x doesn't care about f of a. None of our limits care about what's happening at the specific point. Remember, we only care what's happening on one side, the other, or both. Or we care what happens as we head out to infinity. And so that's really it. Go ahead, review the video if you need to, do the homework, and I will see you in class.